Every year, our phones, our computers, our devices, they get ever so faster. They reach new heights and make us believe that we can do anything. But what if I told you, moving forward, we wouldn't need to focus on making our transistors smaller. We wouldn't need to focus on having more powerful chips to achieve greatness. What if I told you that for the devices that we have now, the next frontier in computing would go completely against the norm? This is where this new niche field in mathematics comes in, topology. You might be thinking, well, what is topology? Topology is a study of math which focuses on the key elements of matter. Topology doesn't look at some of those intricate details. It doesn't focus on those fine points, but rather it focuses on the greater picture, on the final object present. A good way to look at this is to look at both a coffee cup and a donut. To most people, those two objects might seem a little far apart. We might not be able to see the relation to them directly, but to a topologist, those two objects are exactly the same. And why is that? Because to a topologist, they're focusing on exclusively what are those two elements that are the same in this object. Both of these have exactly one hole in them. And due to that, if you were to assume that they were made out of a soft, malleable, rubber-like material, with enough effort, I could turn that donut into a coffee cup, and that coffee cup right back. And what this lets us do is this lets us revolutionize one of the key elements in computing today, conductivity. Nowadays, all of our circuits and all of our phones use elements like copper, aluminum, or other metals to transfer electrons and electricity to various parts in circuits. What topology is going to let us do is going to allow us to unlock a new, different type of material, a topological insulator. What this material is able to achieve is simply amazing. A topological insulator can act as a perfect conductor on its surface, and yet internally, it shows perfect resistance. This duality can help us change the way we approach computing, because no longer would we have to worry about any defects in the material. We wouldn't need to worry about those small intricacies. It's only that surface level which we have to worry about, and topology acts as almost like a self-repairing road. An electron would never have to worry about what's in front of it, only where it has to go. But why is this useful to us now? It's useful to us because it lets us achieve a whole new frontier, a frontier of quantum computers. And the reason a quantum computer is so special is it's because of the way it functions at its deepest level. But before we get to that, we can actually talk about how our own computers function first. And as a matter of fact, we can demonstrate it with the audience itself. I want to ask, would I be able to get one member of the audience to help me out here? Could I get a hand? Perfect. You can just stay right there. I just need you to do one quick help for me. I have a coin with me. I'm going to flip it in the air, right? And as it's spinning, just call heads or tails, and then we'll see if it's going, all right? You ready? Right on the spot. We got a heads from the man in the front. And what he exhibited right now is exactly how every single modern machine works today. We took our coin, or in this case, our bit. A bit is the key element of data in a computer. We flipped it up in the air, we processed it, and we got our final output of a heads. What this shows us is that our modern bits today work in a series of on or off. This on or off stage is how we process every single piece of data today. But what it does come with is limitations. We need to spend so much time waiting for this coin to process, for this data to fully go through for us to work with it. And a quantum computer breaks that norm. A quantum computer works with the concept rather than the final output. There are these special bits called qubits present in a quantum computer, and what that does is that as the coin is flipping through the air, a quantum computer can work with the idea that it can be both heads and tails and everything in between at the same time. We are no longer bound by 0 and 1. We are only bound by our own imagination. And this comes in incredibly useful when processing data. If you think about it now, we can have any series of numbers present and work with it at our fingertips. Our processing speeds will be so much faster, it'll seem almost instantaneous. If we pair these qubits together, if we entangle them with each other, then what we're able to achieve is a whole new level of computing which was unfathomable from before. But all of this comes with one huge caveat. A qubit needs to hold its state, a quantum state. And this state is so incredibly fragile. It's nearly impossible for some of the world's best computers today to hold it for anything greater than just a few seconds. Think about it as such. Let's say we're in the future. This computer I have with me right now, it's a brand new state-of-the-art quantum computer designed for users. If I was working on it, and let's say another individual walked past, that step you just heard, maybe even lighter, would absolutely brick my machine. It would become unusable because the state of that qubit, its ability to be in that quantum state would be 100% lost. It would be like balancing a marble on the edge of a razor. It's in theory possible, yet highly impractical. And that's what the quantum computers of today try to achieve. Those machines you just saw, they're stored 300 meters into the earth. They're in some of the world's most isolated places, in laboratories kept in perfect condition, all in the hopes of just holding 1 or 2 bits in a quantum state. Let's connect this back. How does this concept of topology, this field of math, help us reach this new frontier? That's because now, with a topological insulator, with this new form of conductivity, we can achieve true stability. What this material allows us to do is that rather than storing our data in this fragile quantum state, we can hold it in the material itself, in a topological state. This state lets us create a knot. We've all tied our shoelaces before, and some of us have even gone camping. And we know that with a little bit of wiggle room, we're not concerned about my tent going away or my shoelaces becoming untied. It's this stability that's going to allow us to reach this new level. Because within the material itself, we can now chain multiple bits together, and we can really bring it forward into practical use. But you might be thinking, why would this affect me? How can this machine that is still in an almost experimental state affect my life today? Nowadays, machines like these can actually provide great values to human society, for better and for worse. Firstly, in the medical fields, a quantum computer and its ability to work with so many states and so many possibilities, it could allow us to develop new medicines, new vaccines within a matter of days or even months at most. We would no longer need to have human trials, and we could take away some of the dangers that comes with testing experimental medicines. A quantum computer could revolutionize healthcare as we know today. Even forward from this, climate change is one of the largest issues we tackle today and will be tackling in our future. A quantum computer would be able to take into account every single wind pattern, every single current in the ocean, and every single cloud in the world. And with a computer large enough, we could, in theory, model the entire planet. With such great accuracy, we could find the next best possibility of what to do. That doesn't come with its own caveats. I want to ask the audience a question. Does anyone here use a normal messaging app, let's say WhatsApp or Google Messenger? Quite a few of you. And do many of you guys have passwords and other key information that you don't want other people to access? I see quite a lot of raised hands. One of the big ways that all of this information is kept private to you is through a method of encryption called RSA encryption. In simple terms, what this does is it takes a really large number and it factors it down to two of its largest primes, a prime number being divisible by 1 and itself. And in this case, a normal computer would need so much energy, so much computing power, that it would be practically impossible. There's no one in the world that would think about spending so much time just to decrypt a small little piece of data, which we might not even know what it is. A quantum computer, on the other hand, as we know from before, can simulate every single number between 0 and 1. So what's stopping a quantum computer from just being able to work through every single combination, every single value, in such short notice? In theory, that would allow users to break banking information on anyone in the world, get access to absolutely anyone's passwords, and privacy as we know today might be gone. But that's not to say that it doesn't have some benefits. But the biggest question we have to ask ourselves today, and especially now, is with all this power comes such a great responsibility that we need to ask ourselves, who's going to hold this responsibility? Right now, there are only a few private corporations that have the funding to pursue a project like this. There's only a few universities in the highest echelon that have the students and the population to tackle these new problems. But can we trust them? How do I know that a private corporation, a government, a school, a university, or anyone in the world with this amount of power would have society's best interests in mind? And that's what we need to focus on now, because soon enough, quantum computers can become a reality. And it's best that we answer that question before we get to the huge problem. But I know a lot of what I've been saying has been quite abstract. So let's take a quick step back and recover some of the key takeaways from this talk. Topology is no longer limited to being a niche field in math. Topology is now what's going to be able to help us break through a lot of the computational barriers we face today. Topology isn't just about shapes. It's now about shaping our world.